Now we prove the penultimate step, namely that XMU is a measure space. And then in the next step, we identify the relation between lambda and, so that would complete the Riesz representation theorem. Or in other words, we will say that this is precisely the measure space, that is XMU is precisely the measure space induced by the non-negative linear functional lambda on CCX. Okay, so that identifies it. So first thing, lambda is induced on CCX, or lambda on CCX induces or leads to a measure space XMU. That means there exists a sigma algebra M on X, and mu, as we have defined here, turns out to be a measure of it. And this is precisely the measure induced by, and in fact, we show that mu is unique. I mean, that we have already shown in the beginning itself. So we now complete the existence of this measure, and we have already proved that it is unique. So there, lambda induces a uniquely determined measure on X with the sigma algebra given by script. Okay, and that is the main result. That is the Riesz representation theorem. Okay, so we will work on that. Now let me just recall the definitions systematically one after another. So we begin with a locally compact Hausdorff space X. Now for any open set V contained in X, we define mu V as supremum of lambda F, F subordinate to. Okay, this essentially tells that F is an element of CCX. F is bounded, is non-negative. It is bounded by 1, and the support of F is in the open set. And you can show that this is well defined. There is no problem. Now, using this, okay, one can define mu on every subset of X. That is on the whole of Px that we are able to define this. What you do is enclose this E inside an open set, and then for open set mu is defined. Then you see that this the infimum of all these mu's on open sets containing E will be designated as mu E. You can show that this exists and very well defined. Okay. Now having done that, we define a collection of subsets of E. Now this is on the whole of Px. Now we pick out a subcollection of subsets of X defined by mu F. Now which are those subsets? They are subsets of X with the property that the mu of E is finite and the mu of E is precisely equal to supremum of mu k contained in X, where k is compact. What does this mean? If you look at it, it talks about only those subsets E for which mu of E is finite. Secondly, the other condition is that this mu of E can be obtained as supremum of mu k contained in E. That means take E, any E, it contains an compact subset. In fact, it contains several compact sets. Now, for each compact set being a subset, now you know how to define mu. And then you show that mu E, or you define mu E as supremum of mu k contained in, not defined as, mu E identified as supremum of mu k contained in. Okay. Now this is what it is. So we have the path we have traced is this. Started with lambda defined on CCX, which is non-negative, and using that we defined for every open subset mu. Then using that we defined mu for every subset. Now therefore that is valid for all subsets of X, that is on the power set of X. Now we restrict. Okay, so we start with lambda to mu E to, we define the subsets, the subcollection MF contained in EX X, that is, they are all subsets of EX, not every one, but a collection of subsets. For instance, as I said last time, that if in some cases X may not be, okay, especially the Lebesgue, you take the case of Lebesgue measure. Now you see that if on R, so mu of R is infinite, so that is already ruled out. Okay, from this. Okay, and you see that this is true. So you have the collection of subsets for which mu of E is finite, and this is true. That means such sets for which mu E can be obtained also as the supremum of mu k or k contained. So we have two situations. This is E. Now we are talking about open set V. Okay. For all open sets, mu V is defined. Using that, we define mu E, and then we observe that the next stage is we pick those E for which mu can be obtained as the supremum of mu k, where k is contained in E, and also mu E is finite. Okay, so all those E for which this is true. So this is the scenario that you have. Okay, as I said, one of the properties that you can prove is that mu you have defined is having the property that it is countably subadditive. Mu is countably subadditive on Px. Now the restricted class MF. So mu is countably, this is subadditive, this is additive. On so this is a subcollection that we are collecting. Okay. Then the next step is defining M. M we have defined as the set of all E contained in X with the property that E intersection K is in MF. For every K that is compact and contained in X. So you take E, take its intersection with any K that is compact in X, okay, and then you can actually compute mu of that and then check whether it is in MF. So all those E for which mu of or E intersection K belongs to MF is M. So that is the definition of now X may not be why I highlight this point is that MF may not be a sigma. Okay. Now you take definition of M using MF. So M is not a subcollection of MF. M is a subcollection of Bx with the property that M, any element of M has the property that its intersection with every compact set is an element of. Now we have got the scenario that M is a sigma algebra and mu this is exactly what we want to do. We have done most of it. In fact, last time we proved that M is a sigma algebra. This part we have already worked out. Okay, now before we take up proving the last part, namely on the penultimate part, we prove the following. Okay. That is, we have completed up to 7 steps. Now, up to this we have achieved in now we prove the step 8. What is MF in terms of M? Because we have seen that the elements of M may not have mu finite, whereas elements of M must have mu finite. Therefore, we prove the following, that MF is precisely those E belonging to M such that mu of E is finite. This is the main result that we proved. So we are reworking or finding out what exactly, or trying to understand more clearly what MF is. MF, as I said, MF is not a sigma algebra in general because X may not be in it. As we have seen in the case of Lebesgue integration on R is not in the corresponding because the measure of or mu of R is going to be it. Okay. So let us prove this result. Okay. We start with an element of MF and then show that. So, first thing that we want to prove is this is the result then. Okay, so this is our claim. So take any E belonging to MF, K compact so for every compact set E intersection K belongs to hence belongs to M. Now you see what you have is this. How do you get this? We have seen that if you look at the structure of MF, all open sets with finite measure, finite mean belong to MF. So also all compact sets belong to MF. Okay, so this is already in MF. E is given to be MF, and we have shown that E intersection K or MF is closed under intersection, and therefore E intersection K is in. Okay, so that we have already. Now the next thing that we want to prove is the converse. The converse statement is the following. Okay. So we want to show that the set M, the converse, M with finite belongs to okay. So we prove this. Okay, assume E belongs to M and mu of E is finite. So then we claim such E's belong to. So we prove it as follows. Now we choose epsilon plus. Then there exists an open set V containing X such that E is contained in E and mu of V is now by the third step, by 3 or what I call step 3, by step 3 there exists a compact subset K of X with K contained in E, K contained in E and contained in E such that mu of so you use the two definitions of mu B is there, mu K is there, and then one is in terms of supremum of lambda f and therefore it is the infimum of mu, and the other one is the supremum of mu K. So use these two together to get this result. In fact, you can have this K inside E and K inside this problem. Now, since E intersection K is an element of F, because that follows from the definition of M, there exists, right? Take here the K contains. There exists a compact set H contained in E such that mu of E intersection K is less than mu of H plus H. Find that E intersection K is in MF, and you have H is contained in E. H is compact, and therefore this result holds. Okay. Since E is contained in E intersection K union E minus T. Okay. This is how it looks like. So you have got E. This is K. This is your T. This is your. This is your. Now E intersection K. E intersection K is this portion. This is E intersection. Okay. And V minus K is this portion. Okay. So you have this. You are taking the union of this entire thing. Now the only thing you are leaving out is this portion, and therefore E is now a part of this. Okay. We have mu of E is less than or equal to mu of E intersection K plus mu of E minus K. Now this is less than H. Okay. This is less than mu of H plus mu H. That's very easy. So H is a part of. Okay. H is compact. Okay. Therefore, this condition is satisfied. And this is a part of this epsilon. Therefore, you get H plus 2. Right. So all that we wanted to do was that mu of E is finite. Okay. That completes the proof of part 8. So we have shown that we have already seen that M is a see the crucial point was whether it is going to be of course countable union of subsets or elements of M is in M, that we know. And then we have shown that if A is in or E is in M, E complements M. So X belongs to M. Look at the definition. E belongs to M implies E complement belongs to M. Okay. Then we have shown that A belongs to M, B belongs plus A union A complement R A, B complement R A. Okay. Further, union of then union now use this complete E belongs to M implies E complement belongs to M. So you take the you know, you take the complement of, therefore this the complement of this is also in. Okay. So you take any collection or AI belong to them, and then you want to show that, if you want to show that intersection AI belongs to M, what you do is you take intersection AI and take the complement of that belongs to M from this table. Okay. So what is that? Okay. Or intersection of AI complement belongs to okay. What you can show is this union of, see, AI therefore union AI complement belongs to M complement belongs to M. And this is precisely the state. Okay, that's the proof. Further, you also observe that it's a very nice sigma algebra that you have constructed, contains all the important sets in it, and we immediately have the following facts that all open sets are in M. What does this mean? This implies their countable unions and countable intersections are in M. And if you have a countable union, by repeatedly doing this union and intersection, we see that all border sets are. So, your script M is a sigma algebra that contains all oral sets. That is script M. That is a very nice thing, because at least in this kind of scenario, you have on X, you have a topology, certain properties. Now we are coming through what are called the continuous functions with compact support on X. You take this linear space, and on that you take a lambda, which is a non-negative here functional on that. From there we have constructed all this through these various steps. And the sigma algebra so constructed turns out to be something really nice, because it contains all open sets. The entire topology is now on that. Now this in turn also assures that all continuous functions are measurable. Okay, this is the advantage. Okay, the consequence of this is that the all continuous functions are measurable. So there is a very rich collection of functions defined on X, which are now measurable with respect to the measure space Xn, or measurable space. Okay. That's the great advantage that we have. Okay. Now what do we prove? The final step. Okay. Step, and after that we have to now connect everything with lambda. That be our final task. So this is the penultimate task. But you see that there is nothing to prove here. All the results that we wanted to get this out has been done. So proof. We already have script M a sigma algebra. Now countable additivity of mu on M follows from countable additivity of mu on MF. Why it is so? See, on MF you see that all the sets have mu finite. Now for that, so on MF you already have countable additivity. Now what are elements of M? So this follows the previous step. What are the elements of MF? The elements of MF are all those M for which mu of M is finite. So note that you take a countable collection of mu's in MF. Then that we have already shown that mu is additive. These sets mu is additive countably. So what are the left out sets? The sets that are left out are those for which mu of E is not finite. And for them, it is trivially true that mu is countably additive. Okay? So you see that the elements and for them obviously countable additivity follows. Right? Why? Because you take this mu of n and say Ek is then this is equal to so Ek does not belong to MS. Now you see that so if E is equal to union A, then Ek is contained in, then what more you get? Get mu of infinity. This is infinity. Therefore, that is there, but this one, Ek mu of Ek is less than or equal to and mu of Ek infinity. Therefore, what happens? The right hand side and the left hand side both have this is what we have equal to. Therefore, you see that countable additivity is almost trivially satisfied. Okay, so mu is countably additive on that, and M is a sigma algebra. Mu is a countably additive, non-negative set function satisfying the property that mu of V1 is less than or equal to 2 mu of 2 whenever this is monotone, whenever Okay, so all the properties required of a measure are satisfied. Thus, what we have is this. That completes our work. So we have completed the existence of a sigma algebra which contains all significant subsets of X and the mu we have defined from starting from lambda is defines a measure on that. Therefore, X M mu is a measure space. Okay, so we link the whole thing back. We connect these two through integrals. Okay, so that is our claim that eventually we are going to prove that lambda f. This is what we want to prove. We want to prove that this is what eventually but true, and that will be our task in the next lecture. So that would complete the of the research. Thank you very much.